Good morning, everyone. We will continue talking about water treatment. And last time we had introduced the topic of desalination. And today I will spend a bit more time talking about desalination and also go a bit more into detail about the technique which is presently in vogue, which is reverse osmosis. And if time permits, I'll also talk about the membrane preparation. If not today, then we will continue in tomorrow's class. Like we discussed last time, and I told you that how if you take a mixture of two solutes, it's always at a lower energy, and it is really mainly because of the entropy of mixing. That's what really drives the entire process. There are also enthalpy effects, but the predominant effect is due to mixing and the resultant entropy increase. If you were to look at, for example, let's say I'm trying to do a desalination. What am I generating? I'm generating pure water from a salty water, and let's say the salty water has a vapor pressure of P, and pure water has a vapor pressure of P0. What would be the vapor pressure of salty water compared to pure water? Will it be more or less?
So less. It will be less,
Less.
sir.
Yeah, it will be less, absolutely. So you can see that therefore this ln term will be negative, and the work term will be positive. Okay, and which means that you have to do work on the system to affect desalination. Now, this vapor pressure data is there are handbooks where you can find it, but also you can actually go to this, for example, this online calculator. Let me just see. Yeah. So this is, let's say I take seawater, which is 35,000 ppm. Okay, so this is given in parts per thousand, not parts per million. So let's take parts per thousand. 35 parts per thousand is equal to 35,000 parts per million. And let's say I take the temperature of 298, and which is 25 degrees centigrade, and I take Kelvin, and I now calculate. You can see what is the vapor pressure of salty waters like seawater, 3076.98. I've actually verified these numbers, and they're quite precise. Suppose I were to go to pure water and keep everything else the same. So let's see what happens to 3076. So it's gone to 314241. So you can see that the vapor pressure of pure water is higher, and this is the value. And anything which you add into the water will obviously suppress the vapor pressure. You can put that value into this equation, and then you can actually estimate the work, and you can actually do it for any salinity. I mean, it need not be only for seawater. It could even be brackish water, or like in the Middle East, the TDS of the water is sometimes much higher. It can be about 40,000, 45,000 ppm. So you can work out what will be the work requirement for this. The ratio of the vapor pressures P by P0 is effectively the same thing as the water activity, because water activity is 1 for pure water when P0 is there, and so P by P0 is effectively the water activity of this salty water. So I can equivalently write this as minus RT ln AW. Now, sometimes you will actually find there are tables which give the water activity data. Or, as I said, if it's not available, just go and get the vapor pressure data, and obtain the water activity from that. Because as we said over here, P is less than P0, therefore also AW is less than 1. And so ln AW is negative. And therefore, again, like in this case, what we expect, that the W desalination will be a positive value, and hence work has to be done on the system to effect desalination. So it's effectively saying the same thing. Now remember that this equation is really obtained from the PDV work data, and under isothermal reversible conditions, I can write it as nRT by P. So I can write this in terms of the equivalent P, and therefore I can then integrate and obtain this. And you can take T out because it's an isothermal reversible process, and that is the one which will give you the least amount of work required. Everything else will require a larger amount of work compared to the isothermal reversible process. Now, let's take, for example, if we really want to actually do a calculation, this data, for example, is available. Okay, I've taken it from one of the articles in Science, but as I told you, you can estimate it from the vapor pressure. So for each of these over here, they have given it in molality, the concentration, not in ppm. Okay, but you can express it in ppm. You can, for example, if I've got 35,000 ppm, this data is for sodium chloride. I can write it as 35 grams per liter or kg. Roughly, it will be equal to 35 grams per liter of sodium chloride. And so if I take 35 divided by 58.5 is the molecular weight of sodium chloride, I'll get 35 divided by 58.5, and you can see the value is 0.598 molal. So you can see from the value that it has got an activity of 0.98025, the water activity. And what you can see is that as you increase the amount of salinity, the activity value keeps going down. So obviously, if I'm trying to produce water, and if the resultant reject water that I get has got a very high TDS, then naturally I will require to do more work to carry that out. Now, when I take an isothermal reversible process like this, it means that I'm like taking an infinite volume of seawater and recovering a tiny fraction of that water as fresh water. So what it effectively means that I have to process huge volumes of seawater to, let's say, suppose I want to generate 1 m cube of fresh water. So maybe because it is an infinitesimal, so for 1 m cube, maybe I'm talking about taking 1 million m cube of seawater and just taking out a tiny amount. So that's really what reversible means, which means that effectively after the desalination, there is not going to be any change in the water activity coefficient, because I've really taken out only a tiny amount of pure water, but I've processed a large amount of water, and therefore that's how I'll let's say generate 1 m cube. I mean, this is a totally impractical scenario, but I'm just trying to tell you what really reversible would mean. So if I now want to calculate the work from whatever we saw, we'll write W0 is equal to minus RT ln AW, and as I've written, for removal of an infinitesimal small amount of water, so that there is no change in the resultant desalinated water. It's got the same water activity. I can put in the values of R, and let's say I do it at room temperature. R is 8.314 joule per Kelvin per mole. Temperature is 298. And Ln, let's say I'm taking seawater, so I'm taking this activity 0.98025, and you can do the calculation. You can see that it will come out to 49.42 joule per mole of water. What is the volume of 1 mole of water?
Sir, 18 mm.
Yeah, 18 ml. Now, suppose I want to calculate for 1 m cube. So, what will I do? I'll multiply this by 10 to the power 6 ml. 1 m cube is equal to 10 to the power 6 milliliter divided by 18. And you can see that it will be, this is the 10 to the power 6 term, and I'll divide 49.42 by 18, and it comes to 2.73. So, it will be 2.73 into 10 to the power 6 joule per meter cube of pure water recovered by this totally impractical reversible process. If you go to any data on plants, what you'll find is that they will express it in kilowatt hour per meter cube. So for that, I will just 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joule, because there's 3,600 seconds in 1 hour multiplied by 1,000 joule in 1 kilojoule. So I get my 3.6 into 10 to the power 6. So I divide this value by this, and then you can see that your work is equal to 0.762 kilowatt hour per meter cube of pure water. Now remember this number. This is a very important number, because this is the theoretical limit, lower limit of work. You cannot desalinate seawater and get pure water for anything less than this value. It's not possible, because we are talking about the extreme end of isothermal reversible conditions. Real situation is different.
If we consider a case where we recover 50% fresh water from seawater, the activity value that we will then have to consider is AWC, that is of the concentrated seawater that is left behind. Its concentration would increase from what? From around 0.6 molar to around 1.2 molar, right? Now you can see that the water activity value would then be 0.9601. So we need to put in this value in the W is equal to minus RT ln AW equation, where AW is now replaced with AWC. You can show that the work required would be 100.88 joule per mole of fresh water, from which we can calculate the per cubic meter requirement to be 1.56 kilowatt hour. This is a lot higher than what we calculated in the previous case for infinitesimally small recovery. We had learned when we were going through the air separation lectures that it requires less work when one goes from an initial pressure P1 to a higher pressure P2 through multi-stage compression as compared to single-stage compression. Do you remember that? Similarly, in the case of desalination, if it is done over several stages instead of in a single stage, the work that needs to be done is lower. If we go back to our previous example of 50% dewatering of seawater, but do it over 2 stages instead of 1, the work term can be expressed as shown here. In this equation, Y is the overall recovery, Ys is the recovery at each stage, and AWC1 and AWC2 are the water activities of the concentrated seawater after stage 1 and stage 2 desalination. Now, you can of course get the values of this activity from the vapor pressure data which we had discussed. So now let us try and compute the value for two-stage seawater desalination, the value of the work with overall recovery of 50%, like in the last previous example, where we had done it over one stage. Since we have assumed that the recovery in each of these stages will be the same, that is Ys. And when I say recovery, it means recovery with respect to the incoming feed at that stage. So we can write the equation as Ys plus Ys times in bracket 1 minus Ys, and that is equal to a total recovery of 50%, which is 0.5. So if we solve that equation, we end up getting a value of Ys, which is equal to 0.293. Now, from this value of Ys, the recovery, we will be able to now figure out what is therefore the resultant salinity of the concentrated seawater after each of these stages. Okay, and that's what is done in step 2. Okay, and you can basically work out that after the first stage the salinity increases from 35 ppt to 50 parts per thousand, and in the second stage it increases to 70 parts per thousand, naturally because 50% of the water has been removed after the second stage. So knowing these salinity values, one can then get the vapor pressures at those salinities, and from the equation one would be able to get the activities at those two different salinities, and those values come out equal to 0.9707 after the first stage and 0.9586 after the second stage. So now we have got our AWC1 and AWC2. So we have to insert these values into the equation that I showed you in the previous slide. Okay, and that's what is done in step 3. And the work comes out equal to 1.336 kilowatt hour per meter cube. Okay, so that's really what it is. Now you can see that compared to 1.56 kilowatt hour per meter cube, which we had got for one stage seawater desalination, here the requirement is lower. Okay, so this is the advantage of doing it in 2 stages. It's not as if it only has to be 2 stage. One can even consider 3 stages or 4 stages or 5 stages.
In reality, what we are doing is that we are really going to be doing desalination through different approaches. And let me tell you that many different approaches are known to do this. I mean, I've just shown it as let's say I can have Y1, Y2, Y3, Y4 as all different methods by which I can go from A to B. My end is always the same. Let's say I'm doing exactly the same thing in all the cases, but doing it by different means. So these would all be really functions of the path, you know. So it would be a path function. How I do it. Now let me ask you. Let's ask the class. Okay, quickly run off what methods of desalination you can think of. What is the first one that you've heard of?
Sir, reverse osmosis.
Yes, why not? So let's put
Reverse
all.
osmosis.
Yeah, reverse osmosis. What else?
So solar desalination.
Yeah. Now, when you say solar desalination, let's put it down. Solar desalination. But effectively, what you're talking about is a thermal evaporation of water, right? That's what you mean?
Yes, sir.
See, solar desalination can mean many things. I'll just put as solar thermal desalination, because you know I can use solar energy to get power, and I can use that power to do reverse osmosis. even that would be solar desalination. But I think what you meant is solar thermal desalination, and this is after all what nature does. What is happening in our rivers and oceans, etc. Every moment, water is being evaporated, and using what? Is using the energy of the sun. That's what we are doing. So the entire water cycle in our world is really based on solar thermal desalination. So yeah, absolutely right. Anything else that comes to your mind?
Fractional distillation.
You're saying fractional distillation, right? But in seawater, I've got only one solvent, right? Water. I mean, I don't have mixed solvents. I've got solute, non-volatile solutes, but I only have one solvent, right? Water. Correct?
Yes, sir.
You'll have to see what you mean by fractional distillation. But again, it is a thermal process. Okay. Anything else? And just think, commonsensically, you don't have to worry about whether you are right or wrong. Huh? Don't get inhibited.
Precipitation of the salts.
Wonderful. Why not? Precipitation. Okay. If there was some method of precipitation, great. Yeah. Very nice. Yeah, think like that. Something else?
Sir, if we produce a vacuum, then the water will vaporize and the salt will be recovered.
Right. But you again, remember, it is still a thermal process in the sense that I'm having to evaporate the water, right?
Yes, sir.
You're talking about vacuum distillation, isn't it? See, they're all, I will put, all the things that you're saying, I will put it as P, thermal. Okay? Anything else?
The bipolar
What else can you
electrolysis.
do? Wonderful. Why bipolar? Just put electrodialysis. Bipolar means a bit different. Electrodialysis. Now, here it's very interesting. You see, in one case, when you're talking about distillation, etc., you are taking out the major fraction from the minor fraction. Let's say my minor fraction is my solute. My major fraction is water, and I'm just removing the major fraction. Whether I'm doing RO, whether I'm doing any of this, precipitation is removing minor fraction. Correct? That's what I'm doing in precipitation. And likewise, in electrodialysis, I am removing minor fraction. Has everybody understood? It's clear? Because it is the ions which are coming out of the membrane. And my water is remaining where it's put. Water is remaining where it is. It's just why I'm pulling out my ions. What are other ways of pulling out ion?
So using ion exchange chromatography.
Brilliant. Why chromatography? Some resin.
Ion
Let's just
exchange
put
membranes.
adsorption. Okay. Yeah, ion exchange membrane is electrodialysis. It could be ion exchange resins, right? Isn't it?
Yes, sir.
I mean, and what will you be doing? You'll be doing ion exchange / adsorption. That's what you are trying to say, right?
Yes, sir.
Wonderful. You see, when you start thinking, then how many things come out? Anything else?
Sir, is doing fine filtration possible?
Wonderful. What is the solid that I'm trying to filter out? What we want to say, it is suspended solids, right? You understood what I'm saying? There is some suspended solids which you are filtering out. Correct or not?
Yes, sir.
Yes, sir.
Yeah.
In filtration, regular filtration. But in RO, I have to remove dissolved solutes. You understood what is there? That we don't call normally as filtration, right? Understood, no? But
Yes, sir.
what you will call this as it's a selective permeation process rather than a filtration, because filtration implies that I've got suspended solids, which I don't. It's all dissolved, but I'm still able to permeate selectively the water and take it out. Okay, but your concept is absolutely right. There's nothing wrong with it. Okay. Anything else that comes to your mind?
So, like,
Yeah?
I know this process may not be that feasible, but like as we are seeing, as we are thinking of thermal methods, we can even see the
Yeah.
reverse. Like by freezing the water, we are still
Brilliant.
separating.
Wonderful. Yes, and let me tell you, okay, that that freeze desalination is one of the methods, and in fact, there was a time when it was also practiced. Okay, and what would be the advantage of freeze desalination? Can someone quickly tell me from anything that you are aware of? What would be the advantage? Latent
Vaporization
heat
is
of
higher.
vaporization is much higher, okay, than latent heat of freezing, right?
Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
in principle, has lower energy requirement because of lower latent heat of fusion, and that is 8p kcal versus 540 kcal. This class has given some wonderful answers. Now, let me show you, okay, that this is a paper. Don't take this paper seriously, okay? I find, when I read these things, I find that all of them have a hidden agenda. When they're writing their paper, they're trying to prove that something that they have done is better than other things. I mean, most of the papers, and they conveniently sweep many things under the rug. They will only tell you selectively a few things. But what is important is, at least what is good, is that the guy has put down various possible techniques. Many of them you have actually covered. Let's say the sun's energy is falling on the water and it's evaporating. Nobody is recovering any energy. Okay? Whatever is the latent heat of vaporization, the sun is providing that, and it is going. Yes, it is true that at some point, the vapors will condense and it will form liquid in the atmosphere. But and obviously it will generate heat again, because it will release the latent heat. But in a sense, we are not recovering that energy. So I can look at the extreme situation. So, for example, like we talked about, 540 kilocalorie per kilogram is the latent heat of vaporization, and whether I'm doing evaporation or whether I'm boiling, the latent heat is not going to change substantially. It will be like this, multiplied by 4.18 joules per calorie, multiplied by 10 to the power 3 kilogram per m cube. Let's say I want to figure it out per m cube, like we did in the previous case. And then I also want to express it in kilowatt hour. Okay, so if I convert all of this, I'll end up getting only kilowatt hour per meter cube. Everything else will cancel out. What you will find is the value is 627 kilowatt hour per m cube. So what it means is that compared to that 0.76 kilowatt hour per m cube that we looked at for a isothermal reversible process, if I were to look at the other extreme of how solar energy is, let's say solar power is evaporating, and don't bother about whether it's solar energy or some other energy, the energy requirement doesn't change. Just because I provided it by solar doesn't change the amount of energy that it supplied. So it comes to about 627 kilowatt hour per m cube. So these are the two extremes that we are talking about. One extreme is the impractical extreme of isothermal reversible desalination, and this is another extreme of what the sun is doing, what is happening in nature, but that's not the way people do seawater desalination. But it's good to get that extreme. So these are all processes where, like multiple effect distillation, what you can do is that in the distillation assembly itself, what happens is that I'm evaporating water, and again that water is condensing. I'm recovering that heat which was released during the condensation of water, and I'm putting it into my next lot of water to preheat the water. So once I start doing, then my requirement is not 627 kilowatt hour. It's a lot less. You talked about freezing. Let's say if you have to use refrigeration, then there would be an electrical power requirement to freeze. They've given some value for RO. You mentioned about electrodialysis. They've given a value. Someone mentioned very fine filtration. What you were really talking about is something like nanofiltration or RO. One of you talked about ion exchange or precipitation. Then there is a thing like gas hydrate. Actually, I can take methane gas, and if I pressurize it and put it along with seawater, the pure water actually forms a hydrate with the methane. That's known as gas hydrate, and that's one way in which you can actually do desalination. And believe it or not, deep in the sea, there's a lot of gas hydrate, that is methane with pure water. And maybe it had formed because of the high pressure conditions that exist deep in the sea. And these people were trying to advocate something which is what they were talking about is absorption or adsorption. What they meant is that suppose I take something like silica gel, which is, we know it's a drying agent. So obviously it can pull in water from seawater, it leaves the salts behind. And this person talks about, hey, we have got the lowest energy requirement. What they forget is that after I've taken the water into my silica gel, I have to release the water. How will the water come out? I have to again heat it. I have to evaporate it. And look, another thing, let me tell you. Nobody is a fool to do the most useless process. Why would anyone do it? Anyone would try to practice commercially what is the most attractive process. And for example, if today the entire world has shifted to reverse osmosis, there must be a reason. So we will try and understand. But you can surely see that thermal desalination can take huge amounts of energy. Unless you have got some source of waste energy, some waste heat, it can happen. Like I've got a big refinery and I'm spewing out heat. Then the smartest thing to do would be to do thermal desalination, because I've got a waste source of heat. I can use it. But if I have to burn natural gas to generate heat, nobody will do it. Why would I do it? Okay. Is that clear to everyone? Did everybody understand?
Yes, sir.
Okay. So let us now go to the process of reverse osmosis, which is what is being practiced world over, even in countries like the Middle East, which require a lot of fresh water. And Middle East, has a lot of oil. And that when during the production of oil and gas, they have to burn a lot of stuff. And earlier they were doing a lot of thermal desalination. But slowly, even under those situations, they've shifted over to reverse osmosis, probably because the advantages were overwhelming. So let us look at why that is the case and what is really reverse osmosis. Okay. Osmosis, of course, we all know, you studied it in school, that if I've got a semi-permeable membrane, semi-permeable means, that is what semi stands for, that it only allows the solvent to pass through.
And if I've got a concentrated solution of a solute, such as a salt solution on one side, and I've got a dilute solution of the salt on the other, then because of the nature of the membrane, only pure water will permeate across the membrane, leaving a more concentrated salt solution behind.
So I can pass the solvent, okay, and because I'm passing solvent and its level is rising, okay, and it will go on till it at one point it stops, and that's the point which we say this height difference is really what is osmotic pressure. That's what we say. Now, what was discovered much later and very smart thinking was that if I externally were to apply pressure so that it's a counter force to the natural process, so what will happen is, and if I gradually increase my pressure to go beyond the osmotic pressure, so I first came here and I reached the osmotic pressure with both these pressures are equal, and then nothing prevents me from applying a pressure in excess of that. So when I apply a pressure in excess of that, now I can reverse the direction of flow. So I can actually take out water from the concentrated solution and it will go into the dilute solution. Of course, in a regular RO process, you don't even have any solution here. It will just basically water will come out, from the membrane. But this is just so that you get a conceptual grasp, and that's what reverse osmosis is. That I'm applying a pressure in excess of the osmotic pressure. Let's first. It's always nice to know the history of these things. The first observation of osmosis, this phenomenon, was done by the French people. This person, Nollet, when 1748, just around the start of the Industrial Revolution. And what he had done was that, you see, at that time there was no membrane that existed except for what you could have probably got from nature. And the people were so smart, they thought that maybe kidneys do some kind of filtration, and that's the job of the kidneys. So they took the pig's bladder and used it as a membrane. So the semi-permeable membrane was really pig's bladder. And they found, yeah, that's what happens. Water flows from dilute solution to concentrated solution. So that's the first observation of osmosis. Okay. Then around 1877, the first measurement of osmotic pressure of a solution was done by this person, Pfeffer.
He again did path-breaking work. When they tried to figure out that how is it that you have these trees, which are so tall, like in California they have the redwood trees, which are hundreds of meters in length, height, and they asked, how is it possible that the water is traveling from the bottom to the top? Can it only be by capillary action? No. And what basically they realized was, when we say transpiration, it transpires from the leaves. What is happening is, like, let's say I've got some nutrients up there on the top of the tree, and water is continuously evaporating from the leaves. And so the nutrients are getting more and more concentrated. So it's like as if I'm forming a concentrated solution. And at the bottom, I have got relatively pure water. So I have actually created an osmotic gradient. And you know that roughly per atmosphere, we are talking about 32 feet is the amount that water can climb. So you can make a rough estimate that if you're talking, let's say, about 300 meters or 100 meters as the height of a tree, so that's 300 feet, and so I'm talking about roughly about 10 bar pressure. That's all I'm talking about. And that will allow the water to travel up. Later on, people started trying to figure out that could one make synthetic membranes instead of these natural systems? Would they do the same thing? And the first demonstration of the process of reverse osmosis That is, someone was smart enough to figure out, let me go in the opposite direction. That work was done by two people in two labs in the US. One was in the University of Florida and the other was in UCLA in California, University of California at Los Angeles. Okay, and this work took place actually around 46 to 55, over 10 years, that they demonstrated it. And then towards the late 50s, early 60s, there were two chemical engineers who were working in the UCLA, and they made the first polymeric membranes, which were all based on cellulose acetate. In fact, one of them happens to be an Indian, Sori Rajan, who synthesized the first membrane. And I missed out one most important person. I missed out Van Top. Have you heard of Van Top?
Yes, sir.
Yes, sir.
Yes, sir.
What did he do?
So Van off equation.
Yes, one is the Van Top equation. And this Van Top is also the first person who proposed the tetrahedral structure for some of these organics. He was an incredible person, Van Top. Van Top actually picked up the work, especially of this person, Pfeffer, all the data that he had generated. And Van Top basically said that there is not much of a difference between a solution which contains salts and if I were to consider it like a gas. And then what he did was that he basically, we know that the gas equation is PV is equal to nRT, and all he did was that instead of the P, he put in a pi and said pi is osmotic pressure. And that is the osmotic pressure that we are talking about. So he was the one who first was able to quantify what is the osmotic pressure of a solution, and he proposed the equation pi V is equal to CRT, where C is concentration, and it is just like PV is equal to nRT, where if I take the V on the other side, I write it as P is equal to N by V RT. And what is N by V? It is number of moles per unit volume, which is concentration. Right? So PV is equal to nRT became almost identical with pi is equal to CRT. Is everybody clear?
Yes,
Yes,
sir.
sir.
Okay. And so let us quickly do an equation calculation. Suppose I've got, let's say 35 grams per liter sodium chloride. We are simplifying seawater to just pure sodium chloride. Otherwise, this is the concentration roughly. And we also know the other thing that Van Top showed us, but is that, when let's say a molecule were to dissociate into constituents, okay, then the osmotic pressure changes. Okay. So if let's say NaCl dissociates into sodium ion and chloride ion, so now there are two ions. So my equation pi is equal to CRT. What I will do is that I will multiply with another term I, which basically is an indication of the number of constituents that are upon dissociation. So with sodium chloride, this value will be 2. If I take sodium sulfate, Na2SO4, the value will be 3 because it will form 2 sodium ion and 1 sulfate ion. If it is magnesium chloride, again it will be 3.
Sir, it is on complete dissociation. Na?
Yes. Now that's a very good point. What I'm assuming is an ideal dissociation. What happens is that we also know that as you increase the concentrations of substances, they may not dissociate fully. And that is known as the non-ideal behavior of, let's say, electrolytes. Okay. And that is given by what is known as the osmotic coefficient, which is osmotic pressure that I actually observe if I do an experiment, divided by osmotic pressure through calculation. The deviation is measured by what is known as osmotic coefficient, which has got a symbol of pi. I'm not considering the osmotic coefficient here, but let me tell you that it actually gets taken care of in water activity. I can do this calculation now. Pi is equal to ICRT. So I take 2 times 35 divided by 58.5 moles per liter multiplied by, now I take the R value, which has the term of liter atmosphere per mole per Kelvin, which is 0.082, and I'll multiply by temperature. And if you do this, you get a value of 29.23 atmospheres, which is approximately the osmotic pressure of seawater. And now you know why reverse osmosis, for example, is a great process, but it's a high pressure process, because I have to apply a high pressure to overcome that osmotic pressure. Now, I can also do the same type of calculations. I know that work is basically the same thing as PV. PV work is equal to RT work, right? So if I substitute W0 with pi V, okay, and now if I divide this term by V, then I will effectively be able to calculate my osmotic pressure pi from this equation as well. So let's say we did, let's say, this calculation, and we came up with a value of 1.56 kilowatt hour per meter cube. Now, what is that work? I can now write it as pi V. Okay, that is work, PV. Okay. So now, if I divide by V, which is the molar volume of water, okay, I can actually then get the value of pi, and you can work it out yourself. You'll find that the value comes to 56.04 bar. That is, I'm talking about this particular condition. Okay, so this is equal to 56 bar, and even commonsensically you can work it out. What am I doing? If I'm recovering 50% water, my osmotic pressure now, because my concentration will now become double, so my osmotic pressure will roughly become equal to 58. If I multiply this by 2, and you can see that this value and this value are comparable. So I can actually do the same thing by this kind of a water activity value, which is of course a much more reliable data. And for that, I've shown you that all this vapor pressure, everything has been worked out. So now you know that if I want to recover 50% water by reverse osmosis from seawater, that I will need to apply a minimum pressure, minimum mind you, of 56 bar. And in practice, in reality, the figure is closer to about 70 bar. So you can imagine that it's a very high pressure process. And so that is really why reverse osmosis requires such a high pressure.
This is the compromise which people have to do. Say, for example, we have seen that the separation work will get less and less when I try to recover less amount of water. So if I'm taking 1000 liters and I recover only 1 liter, obviously I require less energy than if I'm taking 1000 liters and I'm trying to recover 500 liters of water. So the separation work will go down as I'm recovering less. But the problem is that I have to obviously pump more water in that case. So my pumping cost goes up as I recover less. So what you have to do is you have to really look for a compromise between the pumping cost and the separation energy requirement. And I mean, qualitatively, it can be shown as something like this, that there will be some minima, and this is the minima which you'll always try to look for as a chemical engineer. What is the minima in terms of the effort that I am having to put in? All right. Now let us look at some other things related to reverse osmosis, which are very important. Firstly, what am I doing? Usually, the process is done with what is known as a cross flow. That is, I'm passing the feed perpendicular to the direction in which the permeate water will travel. So this is my membrane. I'm passing the feed in this direction, and the water is basically coming here, okay, my permeate, okay, and it shows that it's never a 100% rejection. There will always be small amounts of solute which might also get in, but the majority has got rejected. And then, of course, as the water is coming through, I'm getting a more concentrated brine, and so this is my concentrate. That's what it is. So there are three terms which are very crucial. One is what is known as the flux, because flux is what finally decides that how much of membrane area am I taking, because the membranes are costly. How much of membrane area am I taking, and how much of water am I getting, let's say per unit area of membrane per hour or per day or whatever, whatever is the unit that you choose. So flux, let's say, these people have given it in gallons. I can either express it as flux is measured in liters per square meter of membrane per hour. That will be LMH, liters per meter squared per hour. Many people also give it in gallons, especially the Americans. Naturally, if I've got more membrane area, I'll get more water coming out in absolute terms, but it gets normalized when I divide by the area of the membrane. So that's what it is. And so I can explain this. JV is my flux. I can show it as the permeate flow rate. Suppose I measured it per hour, and I've got my value QP, my volume of permeate that came out in 1 hour, and I now divide by the membrane area, and this is my flux. Now, as I showed you here, there can be some amount of solute which also travels through. It's not 100% rejection. So you need to measure the salt rejection efficiency. And this is what really defines the most important attributes of a membrane. It is that how productive it is in terms of the flux, and also how good is it in terms of rejecting my solute. Because at the end of the day, why am I doing desalination? I'm doing it really so that only pure water passes through. So the equation that is used to define salt rejection, which is R, expressed as a percent, is equal to 1 minus Cp. Cp is the concentration of my solute in my permeate, and divided by C average, where C average is the average concentration in the feed. Suppose I took 35,000 ppm seawater and in the concentrate. So say I recovered 50%, roughly its concentration would have become 70,000. So I take the average of these two, and that is what comes over here, multiplied by 100. So this is what gives you the salt rejection efficiency. It's important because obviously if I'm recovering more water and my concentrate is becoming saltier and saltier, obviously in an absolute sense, more amount of solutes could pass. So only measuring the absolute quantity of solute and the permeate concentration gives you a wrong picture of the salt rejection efficiency, whereas this corrects for it. The third is the recovery rate, which is that what fraction of my feed did I actually recover as permeate and how much went past unrecovered. And that is given by Y, and that is equal to the QP, which is the permeate flow rate, divided by what was my feed flow rate in hour. So this is the fraction which I'm actually recovering. So these are the three important terms: recovery rate, salt rejection, permeate flux. This is what you need to remember. Now, let us try and see what are the very significant developments that have taken place over the last maybe a few decades, maybe the last 50 years. Now, look at this. 1970, which is about 50 years ago, the actual requirement in terms of power consumption was about something like 16 kilowatt hour per meter cube of pure water. And look how it's come down. Today, in the large plants, you can comfortably talk about a figure which is quite a bit less than 5 kilowatt hour per meter cube. So there has been more than a factor of 3 improvement which has taken place in the overall productivity of doing reverse osmosis. And this is what has made the technique so popular. On the one hand, the value, the cost of water has gone up. Water is today quite an expensive thing. You have to pay more for water. And plus the fact that my actual energy consumption came down made the two such that today you can say, yes, I will desalinate seawater and provide water. It is not such a outrageous idea, let's say compared to 50 years ago. Even compared to the time when Dryden wrote his book, and he was so visionary and he talked about desalination. But truth of the matter is that at that time the technology was not at all in a mature stage. Also look at this, which is a direct fallout from whatever we discussed in terms of salinity and work that you require to do. So what happens is that typically, obviously, if I have less amount of salt in my feed water, I require less energy. If I have more amount of salts, I require more energy. As simple as that. Now, if I have for a fixed concentration of my salt in my feed water, this turns out to be the best kind of an optimum in terms of the fraction of water that I should try and recover. That is my recovery percent. Typically, what we're talking about is around 40 to 50%, thereabouts. Why? Because the slope is fairly linear at this point, and beyond that, it starts rising steeply. So there is not much sense in trying to recover additional amounts of water. So this would be the best work in the region where you have got almost like a linear profile. You can see it's fairly linear here, but here it starts becoming non-linear and the work requirement goes up. So don't work here. Although it might sound great that I'm recovering 80% of water from seawater, practically it would not make sense. There is another very important thing that you should remember. You see, I am passing what? Pressurized water. We saw that it can be as high as 70 bar pressure or 80 bar pressure. A part of it is coming out as permeate. The permeate that comes out with not substantial amount of pressure, because it is to overcome all the frictional forces while it is permeating through the membrane. So there's a large pressure drop across the membrane. So what comes out here doesn't have too much of pressure. It has more small amount of pressure, but not a very large amount of pressure. Maybe a couple of kind of pressure. But this concentrate Suppose I recovered even 50%, this concentrate would still be coming out at 70 bar pressure. The question is that should I waste this? And the calculation that I showed you of how much separation work, etc., you do, it does not take into account any loss of what energy in terms of the pent up pressure in the concentrate. So what people have done is that they have devised wonderful methods to try and recover the energy from that concentrate stream. One way of doing it is 70 bar pressure is a very high pressure. It is like taking very high pressure steam, which runs turbines, right? I mean, and that's how we get power. So you could actually take the pressurized concentrate and you could pass it through a turbine and you actually can recover energy from this whole process. So, that's one of the ways in which efficient RO processes have been developed, that you are able to recover energy from the concentrate, from this one. This is my input energy into my feed water. This is my concentrate. I pass it through a turbine. I recover power and then I feed that power here. And so to that extent, I can reduce my energy requirement. Or there is another way in which you can do it. There is something known as a pressure exchanger. So the pressure in the concentrate can be exchanged with incoming feed water. So my feed water gets partially pressurized and my concentrate which I have to discharge, that is getting depressurized. Quite similar to what we discussed, when we were talking about heat exchangers for nitrogen oxygen separation. That's how you always minimize the energy consumption in the process. So that was one. The second is that the pumps today are much more efficient. These pumps today actually they have reached efficiencies close to about 80%. But until recently, and even today, in many of the pumps, the efficiency is about 65%. Typically of a centrifugal pump, that's about the efficiency. So naturally, the amount of power that it is drawing is not the same as the amount of work that I'm actually doing on the feed water, because I'm able to only do it with 65% efficiency, a conversion of electrical energy into mechanical energy. And the third is, of course, better membrane, that this permeate flux, has been dramatically improved in the membranes, and so has rejection efficiency. So today, people can do these processes with much greater efficiency. Now, just to show you a large plant, now look at the size. Each of these that you see, these are membrane elements, and there are thousands of them. So the water is going, it's like mostly in parallel and some in series, these modules are connected up. So this is what is happening now. What you have to remember as an engineer is that it is not uncommon for some of these modules to go bad. They might have got punctured or something happens and the quality of my permeate water drops. So I need to have very efficient sensing devices which can quickly isolate the problem. So I might say, the problem is really in this block. Rest of it is all okay. This is the problem. So then I can try and replace only those modules which have gone bad for whatever reason. Otherwise, it would be next to impossible to replace all of them because the cost would be prohibitive. And you may not need to, just because, it could be that only a few modules have gone back, but it's like finding a needle in a haystack. You have to find it and then solve the problem. Now look at these plants. This is one of the largest plants. It's set up in Israel, Ashkelon plant. And you can see that the energy consumption in this plant is about 4 kilowatt hour per meter cube. Remember, we calculated a value theoretically of 1.56, where I am trying to recover 50% water, Okay. Now, but what we have not taken into account are all the losses that can take place in the system, and also we have not taken into account the pump efficiency. What is the pump efficiency? There is one value here. You'll see it says calculated data. And in the calculated data, they are basically trying to tell you what is the theoretical minimum that is required. And I just took that 1.56 kilowatt hour per meter cube, which we calculated, and I assumed a pump efficiency of 65%. And if you just divide this by 0.65, the value comes to about 2.4. So it's not bad. So compared to that, if you're getting values like 4, 3.6, 3.8, these are very good values. You can see one plant, 2.91. It's almost reached the theoretical limits. I find that there are countless papers who will tell you reverse osmosis is a highly inefficient process. We have got something better. What you need to go back to is the thermodynamics, the actual numbers, and see if what these people are talking about makes sense or are they talking nonsense. This is very, very important, and that's where the role of the engineer becomes very important. You can say, wait a minute, are you aware of what is the minimum energy requirement? Most of these people don't know, these values, and they just talk loosely. So that's one. Also, another reason for these variations, like say there are some plants, of course, which require much higher levels of energy. You can see over here. Some of it could be also due to variations in the feed water salinity. So it could be, that people have found some saline stream which is not 35,000 ppm TDS, or in another case, they might be doing desalination of a stream which has got 45,000 ppm TDS. Naturally, then I can't get the same requirement. The requirements will vary from situation to situation. So bear that in mind also. But let me also tell you that you need not always go in a very bookish conventional way. Like, for example, I'll just share with you some work that my colleagues and I did in my previous institution, where we were trying to put up seawater desalination plants in villages in Tamil Nadu. You can see the water is being drawn in, and then it goes into a tank. This water is turbid and it is being clarified, because you can only put very clear water through the membrane, otherwise you'll spoil them. And then you run the plant and you generate drinking water of a very good quality, and you can see all these ladies collecting the water, seawater, desalinated water. Okay, and now it's done in 2 stages. You won't be able to see this properly. Only you need to follow this thing, which is slightly more bold. The initial seawater salinity was about 32,000 ppm, this one. And then in this particular case, exactly the opposite approach to seawater desalination was taken. In other words, the membranes which were used did not have a very high salt rejection efficiency, but they had a reasonably good flux. So when you passed it through the permeate, it rejected about around 75% of the salts, and one got a permeate of having about 8,000 ppm salinity. And this permeate was once again passed through the membrane module, and now its salinity reduced to 290 ppm. And this is probably the best water that you can drink. That's the quality of this water. So here also it's two-stage, but it's a different two-stage where the water was first passed and the permeate was once again passed. Whereas the two-stage that I talked about previously, the permeate was passed, it was presumably of acceptable quality, and the reject was once again passed to recover more amount of water. So the two stages are not the same. Just to give you some data on the energy consumption for this plant, one of the plants, it can produce roughly about around between 3,000 and 6,000 liters per hour of pure water from seawater. You can go through the what is the feed water salinity, what was the feed water flow rate, what was the product water flow rate, what was the recovery, what was the product water salinity. And then in the second stage, it was passed once again, and now it ended up giving about 120 ppm water. And the overall energy requirement in this particular case was about 6.66 kilowatt hour per meter cube. And the overall recovery was about 28%. Now, why I'm stressing this is that sometimes you have to take a practical situation. Like, obviously, these plants are much smaller than those 100 million gallon plants. So you cannot really compare like for like. Secondly, what happens is that you need maybe a more robust technology, a low-tech solution in a rural setting. So this is a perfectly acceptable solution for a rural setting, and after all, thousands of people are drinking this water, and this is found to be a better solution and a more practical solution. So this is really a two-stage seawater desalination of a somewhat different kind. Okay. Now let me go to a little bit more about membrane. So let us look at, let's say, typically what is a membrane. I've given you the sizes here. You can see that when you're talking about, say, sand filtration, what are you talking about? You're talking about suspended impurities, which are removed with the help of the sand. So you're talking about things which have got a relatively large size. Something like 10 to the power minus 3 meter means you're talking about maybe about 1 millimeter to 0.1 millimeter size. And as you're going in this direction, you're coming to the situation where the size is molecular dimensions. Like, for example, the sodium chloride in my seawater is present as what? It's present as hydrated sodium ion and hydrated chloride ion. What is their size? It's only a few angstrom. So you're talking about those kinds of things which will have to be rejected. So we are traversing something like 7 orders of magnitude in size. Now let's look at something intermediate, like you could look at nanofiltration, which is got sizes which are of the pores which are marginally larger. So they cannot actually reject the sodium ion and maybe chloride ion, but things which are slightly bigger than that, they are able to reject with a nanofiltration. Now, then you can come to ultrafiltration, which is now here, even if you look at with an electron microscope, you will never be able to see the pores. You can only imagine the pores, that there is pores. Even in a nanofiltration, you'll struggle to see the pores. But ultrafiltration, you can comfortably see the pores in the electron microscope. Where is this useful for? If, for example, I've got viruses in my, let's say, COVID problem, and I want to make sure that my water does not have any virus, I can actually use an ultrafiltration membrane with a pore size in this region, maybe around 10 to the power minus 7 to 10 to the power minus 8 meter. And I can block off the viruses. Now, when we say virus, all viruses don't have the same size. They might have a range of sizes. So you can see what will be, you can cut off. Now, bacteria are larger than viruses. So I don't even need this kind of a fancy membrane. I might be able to just go to a microfiltration membrane with sizes in this range, and I can remove bacteria. Why do I want to do this? Because the amount of applied pressure will vary. If I've got a membrane with this kind of tight pores, naturally I have to apply much higher pressures, but I may not need to. Whereas if I'm at something like here, the applied pressure would be much lower. So the overall energy consumption would be less. So that's how you will design a membrane. So when we are talking about an RO membrane, remember that we are talking about membranes with this kind of size. You know that, for example, 10 to the power minus 8 centimeter is 1 angstrom, and that's equal to 10 to the power minus 10 meter. So you're talking about the extremes of size of here. And if you're talking about something like up to about 10 angstrom, you're talking about this. So between 1 to 10 angstrom is what this range is about.